Hello students, welcome back once again. So as you know, in one of the previous module, we talked about propagation of two waves. Okay, in that case, we considered one wave propagating in the positive x direction, and the second wave propagating in the negative x direction. So we had one forward moving wave and one backward moving wave. And we talked about standing wave formation. Okay, when two such waves, one is moving forward, one is moving backward, superposed together, what we got? We got what is called a standing wave or stationary waves. Okay, we had certain conditions that a wave should be of same amplitude, wave should be of same speed, and their wavelength should be of identical value. In such cases, we got standing wave or stationary wave. Okay. So we had two equations, one for incident wave y1 and one for reflected wave or rebounding wave y2. And when they combine together, we got the superposed wave and we got the expression for the resultant wave or standing wave. Why do we call it standing wave? Because there is no propagation factor. Okay, x and v are independent of each other. X and t are containing in separate trigonometric function. That is why there is no propagation at all. Okay, the propagation is not there because time function and x function are in different trigonometric function. Okay, and you can also write it in terms of angular velocity and propagation constant, but we call wave number. Okay, we could also write it in terms of wave number k and angular velocity omega, for which 2 pi by lambda is replaced with k and 2 pi v by lambda is replaced with what is called omega. So that way you can also write the standing wave or stationary wave as shown in the last equation. Okay, both are equally applicable. And we found that we can have the condition for nodes and antinodes. Okay, we had the condition for nodes first. I hope you remember it. Whenever the position along the x-axis that is satisfy n into lambda by 2, those points will act as a point of nodes. What does it mean? That means that if the wavelength of the propagating wave is lambda, then all the points having integral multiple of lambda by 2 will be points of nodes. Okay, here you can see this one is a node, this one is a node, this one is a node. Okay, the first, for example, first point satisfies n is equal to 0, and second point satisfies n is equal to 1, that is lambda by 2, and third point satisfies n is equal to 2, that is lambda. Okay, whenever this lambda by 2 become multiples of 0, 1, 2, those points are nodal points where displacement is 0. Okay. And secondly, we had a condition for antinodes. Antinodes are the points having maximum displacement. And we had the condition like this. Okay, x is equal to 2n plus 1 lambda by 4. But if you place n is equal to 0, you get the first antinode point will be at x is equal to lambda by 4. Understand? You can see in the figure, you get the maximum value. Similarly, n is equal to 1 will give you 3 lambda by 4, that is coming over here. Understand? So this way you can mark each and every point. So we get nodes and antinodes. So this is a continuous process. But in the present module, what we are aiming is, suppose this phenomena is happening inside some rigid walls. We have a thread like this, we have a string like this, and a string is fixed between two walls. String is fixed between two walls, and some sort of oscillation is made in the string. Okay, the string is set into oscillations. Okay, so we consider a string with some length, say L, capital L. and both ends are fixed and it is set into oscillation by some machines or manually or whatsoever you can make it. Okay, so of course both ends are tied up to the wall or fixed rigid support, so they cannot move, they cannot oscillate. So obviously those points will act as point of nodes because always the displacement will be 0. Understand? So that will be points or nodes. Okay, and you can say that those tied points you can consider as node points. Okay, and endpoints are node points. So we consider such a case. What is the difference between our previous discussion and this one? In previous discussion, we had no rigid supports. Only one end we have Weber's rebounding, and we got a continuous standing wave pattern. Okay, but here both ends are containing some rigid walls. Both ends containing some rigid walls. So okay, anyway, we know the condition for nodes are x is equal to n lambda by 2. So of course here first point will be at the first boundary, that is x is equal to 0. That you can get by putting n is equal to 0, of course. But what about the other end? Other end is x is equal to L. So you can straight away write second point is x is equal to L. So that's L is equal to n lambda by 2. So we can write the value of lambda. By rearranging this equation, we get lambda is equal to 2L by n. Okay. So that is one of the possible wavelength that can be excited in the rigid walls is lambda is equal to 2L by n. Here you can see that there are different possible values. Understand? You can put n is equal to 1, n is equal to 2, n is equal to 3 like that. N is equal to 0 anyway, not obviously physically meaningful. So, but n is equal to 1, 2, 3, etc. very meaningful. Okay, see now, suppose you put n is equal to 1 here. What will happen to this equation? We get a lambda is equal to 2L by 1 or simply 2L. What is the physics of this? The physics is simply like that. The string can vibrate within the two walls with a wavelength of lambda 1 is equal to 2L. Understand? We will shortly show you. And such kind of a vibration is called the first mode of vibration. Okay, this is called the first mode of vibration, and that wavelength is shown as lambda 1. Okay, this is one of the possibility that is shown in the visual. You can see in the video. You can oscillate this string in different modes. One of the mode is with a wavelength 12. Okay, so that is what is shown here. In this graphics, you can see that here the string is vibrating with a wavelength 12. Okay, for the complete wave, you should know we need the remaining part also. Okay, the remaining part also. But here, so that means this is half of the wavelength. Okay, the wavelength, complete one half of the wavelength is containing the whole length L. So we can write lambda is equal to 12. Okay, that is the mean. So we define a quantity called the modes of vibration. So modes of vibration is actually this one. In the certain pattern, the string tied up between the walls can oscillate in certain patterns. Certain allowed pattern, you can see permitted pattern. So that permitted patterns are actually called the modes of vibration. Okay, permitted pattern means what? Permitted pattern means because they having a finite length, they are supporting rigid, walls are very strong. So depending on the length of the separation, length of the string, they can vibrate in certain specific wavelengths. So those wavelengths are called normal modes of vibration. And it changes from string to string depending on the length of the string. Similarly, the material by which it is made, depending on many parameters, the modes of vibration can change. So suppose, for example, you have a copper wire, you can have one set of modes of vibration. Suppose you have an aluminum wire, you can have another set of vibration. So like that, depending on the type of cable, the type of string used, length of the string used, you can have different types of patterns. So that patterns are called or style of vibration are called normal modes of vibration. Okay, and when n is equal to 1, we have seen now. When n is equal to 1, wavelength is 12 by n is equal to 12. This is one set of vibration, one mode of vibration. This is the first mode of vibration. Okay, first mode of vibration. It is visually shown here. And that, what does it mean? It means that the entire string will vibrate in such a way that wavelength of the wave set up in the string will be equal to double the string length. Understand? So that is what is the physical meaning of this lambda is equal to 12. Now let us again proceed. Suppose now, and of course this is called the fundamental mode of vibration. Fundamental mode. N is equal to 1 is called fundamental mode, and corresponding to the wavelength, you can also derive the expression for frequency, because if there is an oscillation with a wavelength, so definitely there is a frequency corresponding. How we will find it? We know that velocity of the wave is equal to frequency times lambda. Velocity is equal to frequency times lambda. Lambda we know, so frequency can be found by dividing velocity with lambda. Okay, we can divide with lambda v by 12, because our lambda is 12. So this is called the first fundamental frequency. Okay, this is the frequency with which, or the lowest frequency you can say. First fundamental frequency is the lowest frequency with which the string can vibrate, and that is called the fundamental frequency, fundamental mode of vibration. Okay, so F1 is equal to V by 12. Okay, now again we can proceed and we can write n is equal to 2. When n is equal to 2, what happens? We have to divide with the 2 here. So lambda will be 2L by 2, because n is equal to 2. So that will give you wavelength is equal to simple L. That means total length of the wire. So that is obviously shown in the second graphic. You can see it gives you a complete wave. Okay, one up and one down. Understand? Complete wave is obtained. That is the second mode of vibration. That means that the string can also vibrate with a wavelength given by lambda is equal to L. Previous case we found that string can also vibrate with a wavelength lambda is equal to 2L. Now it can also vibrate with a wavelength lambda is equal to L. And we call it a second mode of vibration, so we designate it with lambda 2. Okay, that is also clear. And the corresponding frequency can be calculated. F is equal to this velocity by wavelength, and that is given expressed as Vf2. Okay, second harmonic frequency. This is called second harmonic frequency V by L. And obviously this is 2 times the fundamental frequency. So you can write second harmonic frequency is equal to 2 times the fundamental frequency. Suppose initially the string is vibrating with a frequency 10 Hz. Now the string can vibrate with a frequency 20 Hz. That is a simple meaning. Okay, 2 times the fundamental frequency, and that means it cannot vibrate with any other frequency than 20 Hz. Suppose initially it vibrated with a 10 Hz frequency, now it will vibrate with a 20 Hz frequency. It cannot vibrate with 11 Hz, 15 Hz or 18 Hz. The permitted frequency of vibration is purely 20 Hz, provided the first harmonic frequency is 10 Hz. Okay, that is also clear, and we call it a second harmonic frequency of vibration of the string, or it's also called first overtone. This word overtone is arising out of some audio system, musical system, and this is another name. First overtone is second harmonic frequency. Okay, and F1 we can call fundamental overtone. Okay, or simply fundamental frequency. And other multiples, integral multiples are called overtones. Okay, and again let's move on. When we take n is equal to 3, okay, we have n is equal to 0, 1, 2, 3 like that, and when you take n is equal to 3, we get what? The excited wavelength on the string is equal to lambda 3 is equal to 12 by 3. So that means you can see the third figure here. You will have 3 bumps like this. The 3 bumps you can see, and the string will vibrate by making 3 bumps. Okay, here the photograph shows the different time instant snapshot. Okay, the snapshot taken at a different time instance are taken together. Okay, the position of the string at different time instance are marked together here. Okay, otherwise you will get only a single figure, okay, single time instant snapshot. Here different snapshots are superimposed together, so it looks like this. Okay, so corresponding frequency you can easily find. F is equal to V by lambda, and that is lambda here is 12 by 3. You place it here. So what we get? Third harmonic frequency F3 is equal to 2V by 3V by 12. Okay. So we got so far F1 we got fundamental harmonic frequency or fundamental frequency. F2 we got second harmonic frequency, and F3 we got third harmonic frequency. Suppose you find the ratio of all the 3 vibrations. You can write like this: V by 12, V by L, 3V by 12. Okay. Again, a slight modification is brought here. You can also write it 1 into V by 12. The second one has 2 into V by 12, and third one has 3 into V by 12. Understand now? So this is in the ratio 1 is to 2 is to 3. So that means what? That means that the frequencies are in the ratio of 1 is to 2 is to 3. Okay. Or what is the physical meaning? The frequencies to which we have excited the string is always in the multiples of integral numbers. Okay. Suppose your F1 is 10, your F2 will be 20, F3 will be 30. Okay. That means you can excite only these frequencies in the string. You can never access a frequency in between 10 to 20 or 20 to 30. Understand? These are the permitted frequencies, allowed frequencies that can be possibly excited on the string. Okay, these are very interesting. Okay, these concepts will again come back to you in the quantum mechanics chapter, where you will study about the discretized value of energy, discrete photon concept, etc. Where this discretization will again come into the picture. Okay, and that is what is written here. The frequencies of the mode of vibration that can be excited on a string is always an integral multiple of fundamental frequency. Okay, if suppose if this is vibrating at 5 Hertz, the second one will be vibrating at 10 Hertz, and the third one will be vibrating at 15 Hertz. So 5, 10, 15. So it goes on like that. Suppose the first one is vibrating with some fractional values, say 0.5 or 10.5. So it corresponding multiples will be applicable for the second and third harmonics. Okay, so that is clear. And these integral multiples of fundamental frequencies are called harmonics or overtones of vibration. That already we discussed. Okay, so in general, the harmonics of vibration that can be excited, okay, that can be induced on a string is given by Fn is equal to n into V by 12. Okay, already we have seen explained thoroughly. So in general, we can write any harmonic frequency that can be excited on a string is equal to n into V by 12. What is V there? V is the velocity of the wave along the string. Okay, V is the velocity of the string, velocity of the wave along the string. That velocity will depend on different factors. You keep in mind, it will depend on the type of material by which the string is made. It will also depend on what is called tension on the string, how strongly you have tightened or kept the string. Okay, we have a separate module to discuss on the velocity of wave along a string, where we will talk much detail about how velocity and material parameters are related. Okay? And corresponding wavelength, general expression for wavelength is given here, lambda is equal to 12 by n. And of course, as I told already, fundamental and higher harmonic generation has lot of physical applications in many areas of physics, like optic, quantum physics, acoustic, communication, electromagnetics. For example, in optics, you suppose you have some fundamental frequency of laser. By passing this laser beam through certain materials, you can create higher harmonics. Understand? So that simply means that suppose you have a red color laser, you can convert the red color laser into some green color or yellow color or blue color depending on the type of harmonics you create. So only thing is that you need some materials, some transparent crystal materials, through which by passing certain laser beams you can produce harmonics. Okay, different other colors can be easily generated. In quantum mechanics, of course, you will deal with the harmonics in the case of vibrations of molecules, complex molecules, atoms, in nucleus, this will be applicable. In many cases, the concept of harmonics will be, or fundamental modes of vibration will be applicable in atomic and molecular physics. Of course, in acoustic, no doubt, you have to use this concept of harmonics in generating musics. Okay, generating musics in different types of string instruments, percussion instruments. Okay, where this will be highly applicable. In communication, electromagnetics, and mechanics, no doubt, we have come across different examples for mechanics as well. And in, for example, another good example is that of a microwave oven, where you use microwave radiations that is put in some chamber where standing wave patterns are allowed to exist, and the cooking can be made very easily. Okay, we will discuss one such problem related to standing wave problem formation in a microwave cavity. Okay, so here the entire modes of vibration. The first three modes of vibration of a string is illustrated beautifully. You can see for first wavelength is 2L, second wavelength is L, and third wavelength is 12 by 3. Okay, these are the different modes of vibration, and you can go on explaining n is equal to 4, n is equal to 5 like that, depending on the availability of the exciting device. Okay, you need a powerful exciting device. Using that, we can excite so many model vibrations on a string. So let us recap once again what we have done. A vibrating string fixed at both ends can support standing waves of only certain specific wavelengths. Okay, that is clear. Only certain specific wavelengths can be excited. Okay, you cannot excite any arbitrary wavelength. Any arbitrary value you cannot excite. Only specific value. Some integral multiples only possible. And the string can support only certain wavelength defined by the expression. Okay, so all the vibrations follow this fundamental rule. Okay, length is very important, and the model number n is equal to 1, 2, 3, etc. is also very important. Okay, and such supported waves are called normal modes of vibration. Okay, it's a very important theory as far as many of your future discussion on many physical phenomena is based on this modes of vibration concept. Okay, applicable universally in different areas of physics, starting from the very fundamental nucleus of an atom to gigantic structures. This is applicable. Okay, and keep in mind that this modes of vibration are not only applicable for linear things like springs, wires, rocks, etc. It is also applicable for surfaces and membranes, two-dimensional surfaces, three-dimensional surfaces, three-dimensional objects, you can apply this model vibration. As an example, the model vibrations of certain two-dimensional membranes are shown there. Membranes are nothing but a simple flexible elastic type of surfaces. On that surfaces, you can excite certain model vibrations. Okay? Mode 1 is shown here. You can see the mode 2, how the vibration happens. 2 bumps you can see, up and down bumps you can see. And as you come to the third model vibration, you can see how this is happening. Okay, the difference you can identify, and mode 4 vibration also you can see. Okay, so in this way, these model vibrations or normal model vibrations are applicable equally for one-dimensional, two-dimensional, and three-dimensional objects. Okay, and so it is illustrated here to convince you the matter that this is applicable for all type of structures and bodies. So now here is the time for assignment. We have this question, a very simple question. A straight string rigidly fixed at both ends has two successive normal modes with wavelength 0.44 meter and 0.55 meter respectively. Identify the mode numbers and determine the length of the string. Okay, how you will do it? You have a string, it is vibrating, it's two different modes. It is not mentioned that it's first mode or second mode. It may be any mode. Okay, any mode. Modes are wavelengths are shown here. You have to find which mode is that. How you will find? Very easy. You have the expression for mode vibration, wavelength and mode. Okay, keep in mind that as the mode number increases, the wavelength should decrease. Suppose we assign 0.55 meter for mode n, then you have to assign 0.44 meter for mode n plus 1. Okay, keep in mind, as the mode number increases, wavelength should decrease. Understand? This fundamental principle should be in mind. Okay, so with that concept in mind, you can apply the given values to two equations. You can solve it. When you solve these two equations, you will get the value of n. That is the mode number. Okay, then you can write mode number for 0.44 meter watt and mode number for 0.55 meter is what. Okay, that is the first part. And secondly, length of the string is asked. How will you find the length of the string? Yeah, of course. Once you get n and lambda already known to you, you can easily find the length of the string. Okay. In both cases, L should be same. Okay. Anyway, you can convince yourself, work out separately, and ensure that confirm yourself that L is same. Okay. So this is a very beautiful, nice problem. You do it with enough diagrams, if possible. For your assistance, some value answers are given in. This is shown here, but you do it yourself. And here is the second question. The cold spots in a microwave oven are found to have a separation of 0.5 centimeter. What is the frequency of the microwaves? Assume velocity of the microwave is equal to 3 into 10 raised to 3 meter per second. Okay, this can be also done. So see, it is given that different nodes. Okay, cold spots are actually what? Nodal points. At nodal points, temperature will be low because amplitude is 0, and antinodal points temperature will be high, as you know it very well. Okay, this is clear to you. So you take any two nodal points, say this A and this B. Okay, this distance is given as 0.5 centimeter. Okay, so how will you do it? You know that nodal points are defined by this equation. X is equal to n lambda by 2. So first point you take as 1 lambda by 2. Second point you take as 2 lambda by 2. And you find the difference between x is equal to 1 lambda by 2 and x is equal to 2 lambda by 2. You find the difference. Okay, that difference is given as 0.5 centimeter. So automatically you will get the wavelength. You will get the value of the wavelength. Okay. Once you get the wavelength, you can find the frequency. because velocity is given here. Understand? Velocity is given here. Hope you understood the idea. Okay, we need only this equation, okay, expression for node, and first node, second node, you can find the difference between first node and second node, or between second node and third node. Any two nodes you can take. For every nodes, general equation is given here. So using that lambda, it can be found. Okay, don't confuse that this 0.5 centimeter is not lambda. It is the nodal separation, distance between two nodes. Okay, so I hope the explanation is sufficient. You can do it very nicely. Okay, so with this remarks, we can conclude. And I'm sure that this is a very interesting video, one of the interesting video, and interesting concept too. So you please watch the video thoroughly, make the ideas very clear, because you need this concept in future course of time also. In your entire study of physics, these ideas are very important. So once again reminding you to listen the video completely, thoroughly, as many times as possible until the ideas get concrete too. Okay, so with these remarks, signing off. Thank you.